Hi again. I want to go over a second problem on the integrated rate law. In this case, we have a data table of concentration of the starting material versus time. Once again, how do I know that we are using one of the integrated rate laws in this problem? Let's see. It says for the reaction N2O5 going to NO3 plus NO2, the following data was collected. They want us to figure out the order of the reaction along with the rate constant. And, oh, there it is. If you want to know the concentration of the starting material at a certain time point, most likely you are going to be using one of the integrated rate laws. In a previous video, actually labeled problem 1 on integrated rate law, I listed the 3 integrated rate laws that you should be familiar with. And if you graph concentration of the starting material versus time, and you get a straight line, then the rate of order is going to be 0th order, and so forth. So what you're doing is you're plotting the data, this data, and determining what is the y-axis that gives you the straight line. Is it concentration of reactants? Is it the ln of the concentration of the reactants? Or is it 1 over the concentration of the reactants? Let me show you how I would quickly or relatively quickly try to figure out if I have a straight line, right? Because I want to literally know what the plot of this starting material versus time. Is it straight? Is it a straight line? That's my main task right now, because I got to figure out the order. When you're given data like this, you could definitely graph it if you have time, but on an exam, what you want to do is you want to figure out, is the change in the first, like 25 seconds, identical to the change in the last 25 seconds. That would indicate that the slope is identical at the beginning and at the end, and that's what we want for a straight line. I am going to do data point 2 minus data point 1. So this is 0.822 minus 1. So there was the difference of minus 0.178 over the first 25 seconds. Basically what we're doing is we're looking at rise over run, which is the slope. Over here, the difference is 0.210 minus 0.255. So the difference is minus 0.045. Those are not the same. Minus 0.045. So our conclusion is that the slope is not consistent over the full range, meaning that this does not give a straight line. Not straight line. Okay, so in real life, what we would do is we would want to now plot the ln of the starting material versus time, which means that, yes, we do have to pick up ln. ln of the starting material over time, and again, just pick the first 2 data points and the last 2 data points. Therefore, the ln of 1 equals 0. So I have a 0 right there. The ln of 0.822 equals negative. Don't worry that it's negative. Okay, we're still going to do the same analysis that we did here. Just find the difference in the 2 data points. 196. We might as well take care of this now. So I want to stay consistent. I'm going to take the data point 2, that number minus 0. So I got a difference of negative 0.196. Go all the way down to your last 2 data points. the ln of 0.255 equals negative 1.366 right there. And then the ln of 0.210 equals negative 1.56. Negative 1.56. And actually I'll round to 1, that last digit. Take a look at this difference now. Want to stay consistent, so I've always taken the second data point minus the first, minus 1.561 minus a negative 1.366. Ooh. Negative 0.195. Do you see how those two now are the same? Now what is the slope? It's this divided by the time interval, 25 seconds. The slope, and then slope at the end of the run is this divided by 25 seconds again. So those two slopes are identical. So the slope at the beginning is identical to the slope at the end. What this means is that this data, this ln data, does give a straight line. GHT line. Okay. Which means what? It means that since this equation gave a straight line, but the zeroth order did not, and we can assume now the second order integrated rate law will not give a straight line as well, that reaction is first order. That is your conclusion. Do we answer the question? Determine the order. Okay, so for part A, it is first order in N2O5. That's my first conclusion. What is the value of the rate constant? So to get the value of the rate constants, we got to know that the integrated rate law for a first order reaction is ln, the concentration at some point in time, equals negative kT. That's the important part. It's negative. It's a negative slope, actually. And we knew that. It's a negative slope over here. This divided by the change in time is negative. Plus ln of the initial concentration of the starting material, N2O5. They want to know, they want to know K. How do we do this? This is a straight line, and it's a straight line based on the data that we looked at. So plug in any data point to get K, any data point. Or is it easiest just to plug in time 0? Oh no, we can't put time 0 because that will get rid of this term. So let's pick time 100. Any time point will work. So let's say t equals 100. So we need the ln. Okay, I could do this. ln of the concentration at that time, 0.458, equals negative k. Was 100 the best number to use? I don't know if that was the easiest. ln of the initial concentration, which is, there we go, which is 1.000. We are solving again for k. Okay. ln of 0.458 equals negative 0.78. I don't want to round yet. Let's go for significant figures. 0.7809 equals minus 100k plus ln of 1, remember, is 0. Okay, good. K is positive because we're going to take this number divided by negative 100. Negative 0.7809 divided by negative 100. Okay. 0.00781 equals k. Now it is first order, and you know that you're expected to give the units for k, little k. So the rate, the first order, so the rate law looks like this. Rate equals k times the concentration of N2O5 raised to the first, meaning that that's molarity. So I need k to be 1 over seconds, or seconds minus 1. Okay, let me just make sure that that makes sense. Okay, I'm good with that number. That is part A. We figured out the order of the reaction, and we also got a value for the rate constant with the proper units. Part B. It says, what is the concentration of N2O5 at 250 seconds? Oh, see, they don't give us that number here. They stopped at 200. But we have the integrated rate law, so they want us to know the concentration of A at time 250 seconds. We already have the K. You take the negative of that, 0.00781 times 250 seconds plus ln of the initial concentration, but we know that's going to be 0. We have ln of A t at time t equals, okay, we can do this calculation now, negative 0.00781 times 250. So I got a negative 1.9525. How do we solve for this variable? Good question. We take the e of both sides. So concentration. So from here to here, you take the e. Let me show you what you do with this number. It's e to the negative 1.9525. Boy, I'm hoping that works out. So I have that number already saved, the negative 1.9525. E of that answer equals, thank you. I was half expecting syntax error, but it gave me a number. That concentration at 250 seconds equals 0.142. It is molar. Okay. And does it make sense? Well, you notice here that we're dropping in the concentration of the starting material. 0.310, another 25 seconds, 0.255, another 25 seconds, 0.210, and in another 25 seconds, we're claiming that it drops to 0.142. And I think that makes sense. I think it's dropping at a slower rate each time, right? Very interesting. Oh, you know why this is confusing me? Because we solved it for 250 seconds. There's a gap here. We have 225, and then we just solved for 250. So we got this number right there. That looks good right there. Okay, that is a typical integrated rate law problem where you're given data and you're asked to find the order, the K, and the concentration of the starting material at a certain time point.